Good morning, good afternoon. Welcome to Revitalizing the Grid with Energy Storage Systems. We're so excited that you could join us. My name is Saul Haroon, Director of Renewables at McKim & Creed, and I'm joined with an incredible cross-section of industry leaders to talk about this interesting topic. So we're going to be going on for the next 12 hours on energy storage. I'm sorry, for the next 1 hour. My excitement got away with me a little bit over there. We've seen a lot of evolution in energy storage over the last few years. We've seen supply chain issues, we've seen prices come down, we've seen opportunities rise for energy storage, we've seen the integration of standard renewables like wind and solar. And we really feel this is the year, certainly, where energy storage is poised to make even more impact on the grid as a whole. And so we're going to be going through various challenges, the stacked values of energy storage. We're going to look at planning and designing with energy storage, the evolution of tools, what does the landscape for standards look like, what are policies and incentives, of course, a discussion of lithium, but also other technologies too, and followed by closing statements. So just some housekeeping. We're going to be sharing for the next 45 minutes or so, but feel free to jump in with questions at any point, and we'll do our best to answer them as we're going along or during the last 15 minutes. At McKim & Creed, as I mentioned, where I am, we're an engineering consulting firm with over 40 years of experience in a wide cross-section of engineering disciplines, from civil, surveying, structural, mechanical, and of course electrical and renewable, in a cross-section of markets. I'd like to introduce our panelists, starting with Dr. Sharif Abdulrazik from Duke Energy.
Sure, I'll go ahead and introduce myself. So Sharif Abdulrazik, Director of Renewables Engineering at Duke Energy, focusing on energy storage and microgrid projects. So basically my team is responsible for really cradle to grave for energy storage projects. So for a vertically integrated utility that involves starting from identifying where on our grid are best locations for energy storage systems, and through the design phase, through sizing, optimization, technology selection, all the way through commissioning. And happy to be here. So thanks for the invitation, Saul.
Thanks, Sharif. Excited to have you here. John, over to you.
Yeah, thanks, Saul. I'm John McDonald. I'm the Smart Grid Business Development Leader for GE Grid Solutions. I'm located in Atlanta. I've been working in the power and energy industry for about 50 years now. Been active in IEEE for 52 years. I'm an IEEE Life Fellow and National Academy of Engineering member in the U.S. I think, when we talk about smart grid business development, we talk about an integrated solution for customers, bringing a lot of pieces together from different vendors and making sure they interoperate, they're integrated properly. And that's my role globally for GE Grid Solutions business.
Thank you, John. Thank you for that. Walter, over to you.
Saul, thanks for the invitation. I'm happy to be here. I'm Walt Bucels. I'm co-founder of Waybright, a group of former utility executives like myself. I spent 30 years in the industry, including 10 as CEO of one of the largest publicly owned utilities called JEA in the country, in Jacksonville, Florida. And with other former utility executives, former capital markets investors and managers, former think tank and researchers, and others, we master, develop, invest in, advance the needed transition to the clearly superior, lower cost, more reliable, cleaner technologies and away from the legacy grid, which has served us so well, but is now outdated and relatively inefficient and unreliable versus our modern needs today. It's great to be here.
Thank you, Walt. Thank you for that. So a lot of folks on our call are certainly familiar with energy storage. So why don't we dive right into some of the key problems that the grids and the utilities are facing, and how do you guys feel that energy storage really helps with that? Sharif, if you'd like to start.
Sure. So I think currently the grid is facing no shortage of challenges from resiliency, reliability, and I think what is most pressing is the integration of more and more renewables on our grid, and of course their intermittent nature. I think from our standpoint as Duke Energy, we're as a vertically integrated utility that's managing kind of generation, transmission, distribution. We're very well positioned to basically see these changes in the grid and react to them with our the tools that we have at our disposal. And one of the best tools that we have is energy storage, grid-tied energy storage systems, because you have that capability to operate in 4 quadrants. So there's really a lot of things you can do. So we really, from our end, we started looking at the biggest issues that could be resolved with energy storage systems. So probably in 2017 or 18, looked at our grid and thought, all right, where can we create the most value with a grid-tied battery system? And what came to the top is long radial feeders that really that have customer concentrations at the end and cannot be whose reliability really cannot be improved with your typical wires solutions. So really those projects rose to the top, and fast forward probably 5 years now, we recently put Hot Springs into service, the Hot Springs microgrid, which is 100% inverter based, islandable microgrid that has solar, it has storage, is capable of basically providing backup to the entire town of Hot Springs when an outage occur, and has recently done that since its commissioning. So really, really proud about that project, and many more to come.
I'm glad you brought some good case studies there. I know Duke has been instrumental in engaging with energy storage in the North Carolina areas and I think the entire footprint that you guys do serve. John, as a leader at GE Smart Grids, what are some of the opportunities you're seeing for energy storage from your perspective?
Yeah, I think Saul, when we come home from work, or when we come home and turn the light switch on, we expect the lights to come on. What happens if the sun isn't shining on the PV panels? Or what happens if the wind's not blowing with the wind turbine generators? Who provides that electricity to us? And that's where we get into things like solutions like energy storage to back up the distributed generation that we're interconnecting to the grid. The challenge, though, is that depending on the application, there's different chemistries of energy storage that are more optimal. If it's instantaneous, like frequency response, that's more of a power need. It might be lithium ion. But if it's more peak load deferral, more energy, not power, but more of an energy application, it might be sodium sulfide or other chemistries. So we really we want to optimize. We have to look at the time frame of the application and optimize it. Now, one innovative, talk about case studies, one innovative thing, and we'll see more and more innovation as time goes on, because the growth of renewables is going to continue. The need for energy storage is going to continue to grow. And we're looking for innovative solutions. And I'll provide one that Southern California Edison has implemented right away, was an electronic gas hybrid turbine that has 10 megawatts of lithium-ion batteries integrated with a 50 megawatt natural gas-fired, fast-starting, fast-responding turbine generator in an integrated package with software that optimizes the operation of both. So you have instantaneous response for frequency with the batteries. You have longer term support with the turbine generator. It's optimized. The turbine generator can charge the batteries, So it's an optimized, innovative solution that's implemented. And I think as time goes on, we'll see more and more innovative solutions like that. Because as I said, the growth of distributed energy is going to continue. But again, you have intermittency. How do we deal with the intermittency, and energy storage applications are ideal.
Those are fantastic points. Walt, I know you've got a tremendous experience with utilities like JEA, co-ops, and IOUs, and so on. And now you certainly focused on the financial aspect of things. I'd love to hear your thoughts on this.
Sure. For current case studies, I would suggest there have been many news articles just this week about projects being submitted to DOE. The first round was due last Friday, actually, for multi-billion-dollar grants under the DOE's program to accelerate the decarbonization of American industry and manufacturing. When you read the proposals that have gone public and discussed their proposal and their applications, you'll see there, and in our experience, and we're involved in some of these, what will be common, if not always, will be distributed energy supply first at the plant, at the manufacturing facility, at the refinery. Solar, zero carbon configured fuel cells, other distributed precision power supply at the facility with storage, microgridded, different configurations with grid interconnection based on the circumstances of the area utilities. And that will be, in our belief, and the early news reports about those that have gone public about their proposals, that distributed, decentralized storage, an essential component. We need a bit more progress in bumpless transitions and so forth is coming. There's great work being done by capable people. And those are in those proposals, we believe, we're pretty confident, because it's far less expensive, far cheaper than the legacy grid, far cleaner, of course, and perhaps first and foremost, far more reliable than the legacy grid can be, just because of the physical reality of how the services are provided. So as more and more about those proposals become public in news articles and so forth, I think there'll be some marvelous learning and case studies in those for the use of storage in such large applications.
That's quite interesting. I mean, that leads right into the next topic of some of the use cases, the case studies, and kind of what we sometimes call the stacked values of energy storage, because my understanding is often these benefits come in unison. They're not just isolated. There's also short duration, long duration, and the like. And I know, Sharif, you were quite well versed with some of those stack values. And could you shed a little bit of light on that?
Sure. So, as I mentioned earlier, kind of the first major use case we started addressing at Duke Energy within our energy storage program was reliability improvement for communities that are at the end of long radial feeders. And, when we were designing like Hot Springs, for instance, and the many others, we addressed the primary use case, which was reliability. But then when we started looking at, all right, what is this battery going to be doing the rest of the time? We were able to learn that it's not just that you're going to have an asset that's not operating and producing revenue or value for you as a utility. It's actually that it will degrade faster if operated. So if the battery is kind of sitting there fully charged, you actually get more degradation, and in fact, you kind of risk avoiding your warranty with the battery OEM if that happens. And in this case, we're using nickel manganese cobalt batteries. So it became clear that we need to stack benefits, not just to improve the business case, but to also keep our batteries degradation level manageable. So then we started looking at secondary use cases. All right, what can this battery system do to improve the value streams that it is producing? So we looked at bulk system benefits like, frequency regulation, frequency response, and also kind of some local benefits. But the issue, I guess, we encountered as we were doing this, because we recognized that the grid is not static, right? And that where we're interconnecting the system is not static. There's load coming in. There may be opportunities for a different use case or application in the future. So when we were working with Samsung on the performance guarantees for the system, we told them basically we want to be able to flexibly use this battery and change the use case maybe after year 2 or 3 or whenever. And that basically started a very long effort jointly with Samsung to produce what is now kind of widely known as flexible performance guarantees, right? Which basically describes, all right, if you use this battery in this way, this is the amount of degradation you'll get, and accordingly, this is the state of health we'll guarantee as the battery OEM. But if you change that, you should expect this change in the state of health, and this is the revised performance guarantee or state of health that we will guarantee as the battery OEM. So yeah, we learned a lot through that, and now we kind of have a straightforward way of stacking different use cases, as well as changing these use cases mid project.
So Sharif, is it fair to say that there's almost like a spectrum in terms of short duration and long duration, measured in either seconds in terms of the use cases, or in hours in some cases, or high power versus high energy? And I think something that you've shared before, or you've talked about, is this type of spectrum that's shown on the screen right now for our audience to visualize. Is that kind of a fair understanding, or one way of looking at energy storage use cases, would you say?
Yeah, it's definitely a factor. So duration, or in other words, like the inverse of it, C rate, has a heavy effect on different types of systems. So some technologies, like very high power applications, like capacitors, for instance, they love to operate at very high C rates. Lithium, I mean, it depends on the technology, but some lithium chemistries are better at lower C rates or higher duration, and others are better at or can take higher C rates. So it really depends on the chemistry. And now there's this whole kind of there's a number of now what's called long duration energy storage systems coming out, and we really, as a utility, and really as any party that is getting ready to execute on any of these new products, really have to focus on how exactly these new technologies will operate, round trip efficiency, degradation, fire safety. So really have to look at the full package, in addition to kind of the suitability from a duration or C rate standpoint.
Right. One of the questions that came, and I'm quite sure you can answer it later on, is looking at battery life cycle data, because you mentioned it. I know that's an area of research that you're looking at, degradation and life cycle. So we'll get to that later on. John, as somebody in GE, in terms of looking at it from a systems perspective and all the various equipment and control technology and standards and so on, how do you see these stack values for ESS? What's your perspective on that? I think you might be on mute. So. John, oh, sorry, John. I think you might still be on mute. Can you guys hear? Can you hear us? Okay. John, I think you're on mute. Okay. We can get back to John in a minute. I think he's still on mute. Walt, why don't we dive right into the financial aspect of things
Sure.
with regards to these stacked values? Yeah.
Well, as many would know, the financial incentives, grants, ITC, the Inflation Reduction Act, I wish these had been available when I was a CEO in a utility in the late 90s and early aughts. It is a marvelous buffet of financial incentives of enormous value to further lower the already attractive net cost to the off-taker, to the customer, to the utility when the utility is a significant player. As Sharif is talking about with Duke and that remarkable project in Hot Springs is a national model for what's possible now. But since batteries are, as long as it's renewable energy coming and going, or net zero carbon, say a net zero carbon configured fuel cell, other technologies distributed, it qualifies for the investment tax credits, which can now be as much as 50%, half the cost, reimbursed at commercial operation from the federal government under the Inflation Reduction Act. And for larger projects that are part of the needed and highly valuable industrialization, decarbonization movement in our country now, grants that can be as big as $350 million on a single project under this DOE program we chatted about a bit earlier today. So the financial engineering that can go into these projects now, with storage be an essential and highly valuable part, make the savings versus conventional legacy grid practices even greater than they were before. And so storage is right in there with the actual power supply source, a solar panel, a fuel cell, whatever it might be, and the microgrid qualifying for these incentives and grants. And there are many state programs as well. I don't mean to minimize the state programs that can be very substantial in addition to these federal incentives and grant programs.
Yeah, that's really interesting. And I know our audience is going to be very interested in some of these incentives, some of these programs. And I know in North Carolina, for example, the Desire website categorizes some of these things. And later on, I'd love to hear you talk about where there are clearinghouses where we can access some of this information, get access to these grants, get access to these incentives and so on, to make this all very tangible. John, I know you had some really cool things to say about some of these stacked values. I think you're unmuted now. So, okay. John, I think you're still muted. Shall we? Okay, we'll if you press the unmute button, right. Nope, I think it is still muted right now. Okay. Sorry, guys, we're having a little bit of technical difficulties here. John might leave and come back in. We'll go back to the stack values from GE's perspective in a moment as John joins us shortly. We can get on to the next topic. And what are some of the challenges for planning and actually designing? Oh, no, actually, John is with us. John, are you unmuted right now? Are you good? No, I think it's still muted, John, right now. So, oh, wait, I think you're coming through. Go ahead, John. No, I think it is still muted on. All right, he'll join us shortly. Sorry about that, folks. So what are some of the challenges for planning and designing energy storage systems? Sharif, you've gone through a lot of that experience. Duke Energy has, as you know, as Director of Renewables and Energy Storage. I'd love to hear your take on this.
Sure. Yeah, there's no shortage of challenges, but I think that the biggest one, and I'm sure kind of folks with solar engineering background in the audience will relate to this, but I think the biggest one for energy storage has been really the detailed modeling of energy storage projects. One thing that is unique to energy storage is, at least in this present day, is how expensive battery cells are compared. Like if you look at like the cost of solar panels today, we're talking like what, 30 cents a watt, and you can probably get them cheaper. But for energy storage, I mean, we're probably at that $300 per kWh point or so. Cells are not cheap, and if you look at the overall economics of a project, the cost of the cells, the battery cells themselves, will represent probably more than 50% of the cost of the project. When you look at really everything, the engineering, the labor, the inverters, the switchgear, the cables, really everything, it's just 50%. And then the other 50% or even more is the cost of the cells. So why is that important? It's important because it gives importance to rather estimating degradation, because when you're executing a project, you're either calculating the beginning of life capacity, which is really the number of or the amount of cells you need to purchase on the front end, so that you can degrade down over the life of the project to your needed usable energy for the use case, or you're designing an augmentation strategy if that's how you kind of want to go by things, go with financially. So either way, it becomes very important to understand, all right, for this use case, how will my battery cells degrade versus that use case? And really, what is the optimal technology? Well, not even technology. What is the optimal lithium chemistry and OEM for the use case that I currently have? So I think we have, there are some advancements in that, in that realm being made, and we're leveraging them to kind of move things forward, because otherwise, what do we do as engineers when we have uncertainty, right? We just put in safety margins in all of our designs, and safety margin on top of safety margin on top of safety margin, very quickly projects become infeasible financially. So that's one end of it, right? If you're conservative, as any utility would be. But if you're a developer and you're trying to get a project accepted for kind of the most cost effective way, you're running the risk of your battery system hitting end of life prematurely. So you designed it for 10 years or 20 years, and it's like 5 years it's belly up, and you have an asset that's you're just not doing anything with. So I think state of health degradation, estimation, and just battery modeling in general is one of the biggest challenges today.
Yeah, that's quite interesting. I know we're going to be talking about tools shortly as well. So what I'm hearing from you, Sharif, is that it's a very different world modeling or designing with energy storage than it is with PV. PV's been around for 10 plus, 20 plus years or whatever, and it's a mature technology. Our tools are mature. We understand it. We understand the risk mitigation from that. But with energy storage, there's far more parameters, far more use cases, and far greater challenges in doing so. And I know, Walt, you've kind of touched, you really look into that deeply too. And then we'll move over to John, who will carry on forward from there. So Walt, yeah, go ahead.
Rounded up the engineering economics perfectly well. And the power sources, the power supply, tier one solar panels today, and they keep getting more efficient and lower cost per watt, which is great. Swanson's law. Zero carbon fuel cells, or many things that can be distributed precisely at the customer, at the demand area. The savings for that are so great that adding the cost of storage for an integrated capability to provide the highest levels of reliability and so forth, particularly important to manufacturing, to industrial America and other such applications, with the incentives and all the financial engineering that comes with it. It is far lower total cost incrementally than expanding the legacy grid, building the next transmission line, maybe. That just doesn't make economic sense much anymore. However, and here I see this as perhaps the largest barrier now in our practice. It is that there are some folks and engineers that understand it really, that technical knowledge and expertise. We need more people like Sharif. And so there are ways to get around that to bring in the right team and so forth. But the number of folks that really understand it, it works. It works quite well. It's complex and specialized and different than conventional utility practices are used to, or folks are used to. But accessing that expertise for the organization, it's available, but most organizations just don't have it. There's no reason to have had it in the past. And so you've got to find it and bring it to them to then take advantage of a clearly superior technology for such purposes and applications.
That does make a lot of sense. And John, I think your mic is now operational. Do you want to give it a try as well?
Can you hear me?
Yes, John is right. Okay.
So, yeah, a couple comments. One was we found that one of the biggest challenges for energy storage projects was to really be. We talked about stacked, previously. Was really to be creative, and engineers aren't the most creative in many cases, but what are all the possible benefits? What are all the possible value streams with energy storage? And when we really studied this in detail, we had a long list of applications of energy storage across the time horizon, right, from instantaneous to longer time. And then the question was, what is that application and what are the potential benefits? And also, as I mentioned previously, what are the best chemistries of energy storage? I think that's one of the challenges today is we have an application, but one size doesn't fit all, and keeping up with the technologies as the research progresses. I think the other challenge is having cost-effective energy storage. For a long time, energy storage has been a solution, but it's been above average in expense. The business case in many cases is not as attractive as it could be, as it should be. And I mentioned earlier about the different time horizons and how we should continue to innovate with respect to packaging, like I mentioned, batteries with turbine generators. And the one thing at GE and other companies like us, we've done a lot of work on taking natural gas fired turbine generators and making them much faster to start and much faster to respond than ever before to help manage the intermittency of distributed generation coupled with energy storage. So I think we'll see a lot more innovative solutions. And also, I think we can have stronger business cases if we be more creative with all the possible value streams, the benefits of energy storage.
What I really appreciate about what you said, John, there is this hybrid approach. And really with energy storage, it's not, as you said, one size fits all, certainly not one chemistry, but nor is it just one type of solution fits all,
Right.
one type of technology fits all either. GE has a tremendous expertise in natural gas, or the gas powered turbines, and wind turbines too, I believe, at one point as well. I think that may still be. What I'm sharing on the screen is kind of what John was talking about and what the others were talking about in terms of another visualization of these different use cases as where you are in the whole system itself, right? Whether it's generation, network, consumption, and what type of situation you're looking for: power quality, power reliability, increased utilization, or arbitrage. This from Schmidt and Staffel, Monetizing Energy Storage, a great book, kind of summarized this. Would you kind of agree with that, John? This in terms of what you were talking about, in terms of the hybrid approach.
Absolutely. So this is really what you need to map out is everything from instantaneous to longer time, like arbitrage, you know, peak load deferral on the left, and on the
Right.
right, the location is good. We also I would have a third dimension here on what
Ooh.
are the optimum chemistries,
Ah,
okay, of energy storage for that particular time of application.
that's a great one. You're right. The C factor, the capacity, the ability of the technology, the duration, and so on. Um, Sharif, yes, over to you. I think you've got some interesting material you'd like to share. I'd love to see
Yep.
that.
Yeah. Just touching on the point that John was just making. There is no one size fits all with energy storage. So I just wanted to share kind of real quick something that I recently caught on LinkedIn here. Can you see my screen?
Yes, that's beautiful.
All right. So this post basically, what I really like about, just some background. This
Sharif,
is
sorry to
a,
interrupt. It's a bit fuzzy. Can you, I'm not sure why. Is that a screenshot maybe?
so I should be sharing. Let me see if
Okay.
I was sharing my entire window. So let me see.
Okay.
Do you still see it? Because I don't know on my end. Oh man, it looks like technical difficulties are
Try it
persistent.
again. Try it again.
Uh, it's uh, it's frozen now. Like
Okay,
the
no worries.
like,
In fact, this kind of leads into our next topic on the evolution of tools. And I think you've certainly done a lot of work on that front in terms of evolving these tools to help us model and help us characterize energy storage. Do you want to talk about that and then maybe share the screen again if you can?
Sure. So yeah, here we go. Now I shared my screen again. So
Yeah.
so yeah, we started kind of leveraging uh, like a tool like Storalytics, for example, to kind of model exactly how different batteries will perform different use cases, and also to have a good level of accuracy in degradation estimation on kind of the front end of the design process. So really, it helps us to know kind of through a desktop review day one when we're considering a project, all right, how much degradation will this use case cause, and accordingly, how much should we expect this project to cost us? Especially recognizing again that 50% or more than 50% of the cost of energy storage projects are the cost of the battery cells. Uh, so so that's one point. It's created kind of a huge advantage for us to be able to develop projects. But the other thing I wanted to touch on was kind of to John's point earlier. All right, what battery technology is best, right? And how do you define that? What we found is in order to answer that question, you have to define a use case first. You have to first say, all right, I need a battery to, provide a backup power application. It's going to be doing deep discharges. It's going to be operating, at this ambient temperature, right? It makes a difference if the battery's in the Arctic or if it's in, the Mojave Desert. It makes a huge difference. So only then you're able to kind of put together a score sheet, right? So what I really like about this score sheet, and I'm not sure, are you guys able to see my screen?
I'm going to share now. I found the link on LinkedIn. Great
Okay.
article. And can you guys see my screen? Is it fuzzy or is it clear? So, right. Can you see the link now? So I'm sharing, I think, what you were sharing before. Now, can you guys see it?
I don't see a shared screen, so I don't.
Okay. I think Parker needs to. Hey, Parker, can you share the screen there? There we go.
Oh, there we go.
There we go.
Yep.
Is that now clear?
Yep. It looks perfect. Yep.
Perfect. Yeah.
Very clear. Yeah, I
Great.
appreciate that. So here, really, you see the use cases written there. So they define like the execution strategy, if it's overbuild or if it's augmentation, and then they have like the type of cycles and the number of cycles. So here they just said, all right, high cycle count, deep discharges. I think, for the most part, they're pursuing kind of simplification of the in describing the use case rather than putting like a number of basically numbers really. So only then you're able to see, all right, really, how does this new long duration technology, nickel hydrogen, that Enervenue produces, how does it compare to lithium, right? What's going to be the beginning of life capacity compared to lithium? What's the usable depth of discharge? So for this one, right, their battery system actually allows you to go to 100% depth of discharge because they're basically kind of scuba tank like battery cells. State of charge is pressure based, so you really can go up to 100% state of charge, which folks probably know you can't do that with lithium unless you switch the charging method to constant voltage. So really it's advantageous from that perspective. Also, cycle round trip efficiency, not as good as lithium from that perspective for this type of use case. So it's this is what I was trying to kind of convey earlier. It's important to look at the full picture for your specific use case, not in general, because it makes a huge difference. Because for it, I'll mention another example. So this battery system, nickel hydrogen, it's only cooled by fans. It's not a refrigeration cycle like lithium. So it matters much more where you're putting it, right? Because the performance of the battery system is actually affected by ambient temperature. So that's why, in this simulation, they kind of specified the use case and where it's installed. They're assuming 20 degrees Celsius. So that's really what I'm trying to stress on here, right? You have to look at the full picture and find a tool to do that with.
This is really, really interesting. I love these kind of, like any engineer, we love graphs and charts and so on. I love this kind of categorization or charts of this. Now, this is from a tool called Storalytics, which is, I believe, now available on the marketplace for folks to characterize an energy storage project. Is that correct, Sharif?
I believe so, yes.
Okay, fantastic. Yeah. Yeah, and we can provide a link to that, Sharif, if you like, later on, and share that with everybody too. And there are various tools, just to be a little bit agnostic about this, available in the marketplace for energy storage modeling. Some are tied in to things like microgrids or photovoltaics and so on, like Homer and Zendi and even System Advisor model. And there are others like Fractal and so on that can focus in, and Storalytics can focus in on the energy storage portion. But I think the key here, Sharif, if I'm hearing you correctly, is we really truly have to look at the whole life cycle. We have to look at the use case, we have to look at the engaged technology, and we have to look at the complete life cycle of the project as operating, and then bring in financial metrics too. Is that kind of correct in terms of these tools, what they help you do?
Exactly. So, like, as a brief example, right? So, if your degradation is much more with the lithium technology, you need, much more beginning of life capacity, which means you need to purchase more cells. But if you compare that to another technology with less degradation, and maybe it's more expensive on a dollars per kWh perspective, your overall cost of ownership of the second one may be much less if it's degrading less, and accordingly you need much less beginning of life capacity. So, which I think is the case with this comparison here, because nickel hydrogen is 30,000 cycles. Lithium is about 3,000 to 4,000, and Venue is guaranteeing 20,000 cycles. So it's if you look at it, right, you'll find that your overall cost of ownership is probably going to be less for a lot of use cases with nickel hydrogen.
Fantastic points. I wish we had more time to dive into that. I'd like to kind of switch over onto standards, and I know standards are really critical in making all of this, feasible, viable. So, John, what are some of the key standards today? What are some of the gaps as you see it as well?
Yeah, standards. For many customers, I've been involved with IEEE standards for about 35 years. There's 17 technical committees in the IEEE Power and Energy Society that write over 50% of all the IEEE standards. I would say, first of all, the IEEE 2030 series is probably one of the most important with what we're talking about here. And there's companion documents like 2030.1 is electric vehicle quick charging systems, but 2030.2 is the interoperability of energy storage systems integrated with the electric power infrastructure. So that's, 2030.2 would be an important one. 2030.3 is the test procedures for energy storage integrated into the grid. So .2 and .3 would probably be the most critical in the 2030 series. Then, of course, you have IEEE 1547. We all know that as the from the very beginning, is the rules to integrate distributed energy resources into the electric grid. The one gap we had, though, that we needed to fill was there was a need for a standard for integrating larger distributed generation sources into more of the transmission part of the grid. 1547 was good for sub-transmission distribution. So a new standard a couple of years ago was finished called IEEE Standard 2800. And 2800 is the interconnection and integration of inverter-based resources interconnecting with and associated with a transmission electric power system. So that filled that gap. So I would say 2030 series, particularly .2 and .3, 1547 and 2800 from IEEE are probably the most relevant, for energy storage for what we're talking about.
Yeah, that's certainly quite a tremendous amount of them. I'm going to try to share my screen to summarize or to give a visual representation on some of those here. I think folks can see it right now. These are some of the IEEE standards. Of course, there's also the NFPA standards, the NESC standards, and so on that I think will kind of coordinate and work together to address, and the UL standards, of course, too, for safety operation too. And I think, John, would you say this is a little bit, maybe a bit of an eye chart right here of some of these particular standards, excluding the 2030 and 2080 that you mentioned, I think. There's quite a bit here. We can certainly follow up with folks on some of these standards later on. I think we could devote an entire. John is a wealth of information on standards and IEEE. If you're not a member of IEEE, highly recommended. A shameless plug here for IEEE and the PES, Power and Energy Society, and the smart grids and so on. As we're nearing the top of the hour, I think one of the things that is of great interest to folks is some of the policy and incentives helping this cause, whether it's the IRA, whether it's the infrastructure bill, and so on. Walt, I know you're a wealth of information on that. What are some of these policies? What else do we need, and what financing options are available? All in 2 minutes. Go. No, just kidding.
There's a ton. And so you want people involved on each significant project that are familiar with the industry. For example, we're doing projects with nonprofit universities and colleges to take their campuses to be self-sufficient, microgridded, renewable, including storage, for all the benefits there, in conjunction, coordination with the area utilities and so forth. But I'll briefly touch on in the value stack, depending on the state and how the wholesale markets work. We use at times, if the state's market are done this way, when wholesale hourly market prices go to $1,000, $2,000 a megawatt hour, we set up our storage in the project to be able to, working with the utility, provide our megawatt hours from our storage when it's worth $1,000 or $2,000 an hour. And it doesn't take many hours like that to really supercharge the overall benefits and savings to the various parties that are affected by moving to distributed, precise power supply and microgrids and all of these things we've been talking about. And as part of that, there are now private weather forecasting services available across the country that are deploying advanced sensors and algorithms and so forth, providing weather forecast statistically significantly more reliable than public forecasting data, to be made available to significant organizations with significant storage to further optimize, in this case financially, the charge-discharge cycles, coordinated with, first and foremost, the most reliable electric power supply for Hot Springs, North Carolina, or the factory or the college campus or university campus, as we're doing in different parts of the country. So some of those financial tools and private, really remarkable weather forecasting services that are now increasingly available also should be brought into the analysis and detailed design for a given application. Pardon me for getting off a little bit in some other things, but there's more tools than just the initial essential complex engineering economics. Those financial factors, including incentives and grants and all the rest of it, are really there, but you need the people that understand it to assemble it in a way that optimizes for your application.
And for the type of client in use, whether it's a nonprofit, you mentioned nonprofit, and it sounds like this is the year that nonprofits, religious organizations, universities, public universities, and the like can benefit from the incentives where they could not before. Is that really the case?
Yes, it is so exciting to be able
to
get 30, 40, 50% of the cost of your solar, your fuel cell, your storage reimbursed, paid for through a federal payment to you, your university, your college, whatever it might be, your city. Wow. It just supercharges the benefits to the parties to accelerate it and get going.
Right. Before we go on to the questions, I know a question that always seems to come up is about the chemistry. Is lithium still king? What other chemistries and technologies should we be mindful of? Any one of you want to jump in on that, whether it's Sharif or whoever? Yeah.
I mean, the one I've been really following closely, and I think is a really strong contender to lithium, is nickel hydrogen. I've looked at a lot of battery technologies, metal air, iron air, zinc, EOS's technology, just multiple that are out there. But I think, and I think they all have their own niches. Some are more stronger than others, but really, I think the silver bullet that nickel hydrogen has over lithium is a really strong one. You have like a technology with 10 times the cycle life, slightly less round trip efficiency, slightly more self discharge, but not too much. And really, one of the major disadvantages of it really doesn't matter much for stationary energy storage. The fact that its energy density is much less than lithium. We really, in stationary storage, we don't care. We're not putting these batteries in EVs, right? So I think we're going to be seeing much more of that one in the next probably 5 years. And I'm really excited about it in general.
Right. Yeah, and I know Duke Energy, like several utilities, have been experimenting with different technologies. I think including fuel cells and flow batteries as
Yep.
well, right?
Yep.
An entirely different type of chemistry. Is sodium on the radar as well? Any sodium technologies?
We're looking at sodium sulfur for a pilot project in Florida. So we're looking at that. We're also planning or considering an energy dome project for one of our sites. So we are looking at different technologies, and our emerging technology office, led by Tom Fenimore, is just doing an amazing job in Mount Holly, just getting these different technologies, testing them. I mean, I'm able to provide this feedback about Intervenue because we're piloting their system at Mount Holly, and it's been just doing amazing overall. So really hats off to Tom Fenimore.
It's always exciting to hear about case studies because it all becomes very real, and all that garnered experience then can go back in to further modeling, further evolution of the tools, and further financial metrics as well that can be honed in the future. Maybe we could switch over to the questions, and then after that, I'd love a kind of a closing statement from each and every one of you. So we will go over a little bit over the hour. For those who have time, feel free to stay on. So some of the questions kind of, I see common themes through some of them. So one of the things a LinkedIn user said about highlighting microgrids as an orchestration of these different integrated systems, short-term, long-term, flexible demand, and so on. And I think we're all kind of seeing that too. Microgrids. From a utility perspective, how does that factor in? Because microgrids tend to be often end user or campus level. What would you say? How does this integration look like from a utility perspective, Sharif? Or Walt, actually.
Go ahead.
Walt. Sorry, I'll preempt you. Walt, if you want to say that, and then we'll move on.
It works the best when the utility wants to be a part, to own, if they choose, to operate and maintain where effective, where the microgrid, the distributed power supply, the distributed storage in large, campuses, factories, large applications, is integrated into the legacy grid and legacy utility. And there are a number of case studies around the country already. That works the best in our experience. We always want to work with the area utility. There's so many mutual benefits that come. It's new. Not a lot of people fully understand it or have experience with it yet. So there's some learning to be done. But integrated with the utility to harvest all those benefits collectively, that's the best. Sometimes that's just not in the cards in some states and for different reasons in our projects around the U.S. But it works the best when the utility is a partner and works together with the off-taker. The benefits to be shared are remarkable.
Thank you, Walt. Sharif, your thoughts?
Sure. So we've been looking at kind of microgrids from a, not just like CNI or even city microgrids like hot springs. We've also kind of from an R&D perspective been looking at it from a clustering. So we just basically completed a a project with UNCC and Idaho National Labs, and that had received funding from the Department of Energy to see really how can we cluster our system, leveraging DERs that are different in nature and that are dispersed throughout our system for the main purpose of improving resiliency, improving reliability, and improving also efficiency. So the results of that project is now published. It's called REDIS PV. Dr. Sukumar Kamalasadan with UNCC led that, and it's just it really, I think, touches on or its results touches on the question of the gentleman who asked that question about orchestration of different resources.
If you can share that link, Sharif, would love to, if it's all right, publicly available, would love to share that. We'll have Parker share it on the chat box right now.
I'll send it over right now.
Fantastic, thank you. John, your thoughts on this orchestration?
Yeah, the things have changed with microgrids. You know, the original applications of microgrids were very niche. There were 3 niche applications: university campuses to improve the efficiency of electricity use, military bases, and rural villages. Our first microgrid project at G in 2010 was a rural village in British Columbia, Canada. But things have changed now. Today, the emphasis is on improving the resiliency of the interconnected grid. Okay. And Commonwealth Edison, for instance, in Chicago, is putting in 5 strategic microgrids that are normally connected to the main grid, as Walt said, but they can be islanded and operate themselves. So today the focus with microgrids is resiliency. How do you improve overall grid resiliency? And it's a whole new dimension with microgrids. There's much more emphasis. Look at the Bronzeville community microgrid that ComEd has just published a lot of work on, and they talk about. That's to improve the resiliency of the overall grid. So I see the future being much more emphasis on microgrids, much more use of microgrids, and the connection to the main grid is there, but it can be islanded and have its own generation, which a lot of that is renewable generation to operate independent of the main grid.
Walt, it sounds like you have a thought.
So a quick example is just what John was saying. There's an NFL stadium in the northeastern U.S. that is powered with fuel cells and a microgrid, so that if the area grid goes down, like on a playoff game or the Super Bowl, their power stays on. And so as John was saying, the applications are expanding and growing rapidly for a variety of good reasons, including NFL stadiums now.
Thank you. That does make sense. I'll take 1 or 2 questions here, and then we'll kind of go into the closing statements. I know we're a little bit above the hour. Sounds like we should maybe stick around for another 12 hours until midnight. I know we'd all have a lot of fun. So one of the questions relates to the absence of open data available, such as meteorological data, irradiance, etc., are enabling R&D researchers to create algorithms for next day storage system. I think one of you guys did address that in terms of market available data sets now, and that a higher quality for, I think this all goes down to risk mitigation, right? And appropriate planning for the future and forecasting. And Walt, I think you were talking a little bit about that.
Yeah, I'm not aware of publicly available. There are many private companies that are deploying ground, subsurface, air sensors of very sophisticated data networks around cities and in urban high density areas, and using algorithms that continually improve, producing next day, next week weather forecast of accuracy percent far superior to conventional publicly available. I'm not currently aware of such data being provided in readily accessible, but there are a number of private companies doing it, and the cost for subscribers continues to fall depending on the application in which they're putting it. But there's some phenomenal work going on near-term weather forecasting tomorrow, next week, next month, for such uses to optimize such operations.
Yeah, I'll add one thing. I think as Walter mentioned that yeah, there are a number of companies out there that are providing very accurate meteorological data. I just kind of sent a link to NREL's TMY3 repository that kind of it's open. It's probably not as accurate as the paid companies that are available, but it's definitely something to leverage for research, and I think will provide accurate results.
Thank you. Thank you. Yeah. I see some of the other questions relate specifically to solar or EV charging or air conditioning loads and anti-islanding and so on. I'll be happy to take those offline, Neil and Harry, about those. I think we can move on to the kind of closing statements. Before we do so, I think what relates to everything that we're talking about is what I'm sharing on the screen right now, is this energy storage as helping to transform the electrical infrastructure, our grid, and it just so happens to be that the letter D seems to feature quite prominent into a lot of these efforts. So we're talking about decarbonization, the grid, decentralizing to some extent, the engagement of direct current, a dynamic grid, a distributed grid, and a defendable or having cybersecurity measures in place as well, and of course digitize. And I think this kind of helps frame where we're going with energy storage, with microgrids, with EV charging stations, and all these allied technologies that we are bringing together. But I'd love to hear some of your thoughts on everything that we've talked about. Sharif, if you'd like to start us off with some of your closing statements.
Not really. I don't really have any deep ones, but really like to thank you for organizing this panel. It's like always, very very informational. I always love kind of chatting with Walt and John. So certainly happy we did it, and hopefully it's not the last one, and we'll do many more. So thank you for that.
Absolutely. John, your thoughts on some of the things we've covered?
Well, I would say two trends I think that were in your slide. So one is the moving from centralized to distributed has been a big change for our industry. I've been around over 50 years, and everything was centralized for many, many years, and the challenges of distributing the intelligence, distributing the decision making. Why we need energy storage now, not just in one place, but spread out all over the grid. Why we need standards to help us with that is huge. The thing we forget, though, is we need a strong grid before we think about smart grid. Okay. And what I mean is we need the communications infrastructure to support the distributed nature of the grid. Our communications infrastructure has supported a top-down architecture, top-down communications, up and down, and we need more peer-to-peer communications today to support substation level intelligence, grid edge intelligence, not just at the control center. And that's something that we don't have today. Second thing is the digitization. And that's why people like Walt and I haven't retired yet, and why we're still working. Things are more exciting today than they have been. We were with respect to digitization, we were reactive for decades. We waited until something failed or the transformer exploded, and we reacted. By then, it was too late. Now, what's cool is we're using artificial intelligence, machine learning, digital twins to move from reactive to predictive. We're getting health information on assets. And with analytics, we're looking at the health, and we're preventing failures from occurring, and that never happened before. And that includes monitoring of energy storage. What is the health of the energy? We have battery monitoring systems that we're using all over the grid. So I think those are the two, the distributed, moving from centralized to distributed, and moving from more analog to truly digitization, not just of the substation, but of the whole grid.
Thank you, John. There's a lot of richness in what you're saying, and we do need another 12 hours to dive deeper into that. But some closing statements from you, Walt.
So I'll just second what Sharif said about you and McKim Creed. The projects y'all have been helping us on, your service is first rate, and doing this is so valuable and so welcome. I'll just briefly piggyback what John was saying. The legacy grid that served us so well for 100 years, it needs to be preserved, and it has a long period of valuable service going forward. But we need to stop expanding it. We need to be expanding DER, microgrids, to serve the new loads and the growing loads, because it saves money, it's more reliable, all those things. And not to get too far away from what we're talking about, for our nation's international competitiveness in manufacturing and core industries, we need to be about this in a very serious way, because the cost of energy, including the quality of energy, is the differentiator in international competition. And we need our manufacturing, our industries to be rapidly capturing these benefits for all of those broader mutual benefits for the country going forward. Not to get too preachy, but that's essential in our view, and why this excites us and interests us so much, frankly.
Thank you, Walt. One of the things I really appreciate about all of you is certainly you've got your areas of expertise, but you've recognized it's the collaboration together collectively that we can advance the community forward. Now I'm just using all C words: collaboration, community, and collective, so to speak. And I think that's something which has been an honor and continues to be an honor working with all of you and the greater community at large that has joined us and beyond in moving forward the advancement, so to speak, or the intelligence of the grid. And of course, we didn't even go into AI and all this other and data analytics and so on. That's all part of that parcel too. So there's certainly some really interesting questions, and I will take them offline. And there's I feel we've just of course, just touched such a deep reservoir of topics that we need to get into. So this is one in a series of panel discussions that we will continue to have. So please stay tuned for future panel discussions with our leaders right here and others too on this topic and allied and related topic. So once again, thank you, Walt. Thank you, John. Thank you, Sharif, for everything, for this panel discussion, but also for everything that you guys continue to do. And I think it's all right for our audience to reach out to each and every one of you. Feel free, everyone, guys, you can reach out to us, and McKim Creed will connect you up to our panelists and to others as well. So please keep the questions coming, keep the ideas coming, and understand this is a continual spectrum of discussion, of dialogue in advancement of energy storage, of microgrids, and all the allied technologies too. So once again, thank you so much, and we look forward for you tuning in the future.
Thanks.
Thanks.
Thank you.